Okay, welcome to the OAI panel. And I think yesterday in the Meta exec talk, I had mentioned something like AI workloads, right? The model complexity, the model size are actually growing exponentially, and we need a significantly more capable hardware and scalable high-performance hardware. And so here, we are gathering the expertise in the industry, and then talk about what should we do, and then what are the challenges we're facing, and what are the opportunities we are seeing, and what can we do, right, in terms of like utilize OCP platform to do something useful and shape the industry. Yeah, so here we are. Okay, I'm gonna, maybe we should get started to introduce ourselves in a bit. Yeah, Brad?
Yep.
Yeah.
Maybe I just want to start off by saying we have one panelist who's not here, Rob Ober from NVIDIA. His feedback to some of the discussion topics, we will post it on demand, so this won't be available right now, but once Rob has his video in, we ran into some logistical hurdles. So we will have Rob's info added after the event. I'm Bharat Mutaya. I'm part of the infrastructure team at Meta, and I handle technical sourcing of server and AI technologies.
Hi, I'm Sailaja. I'm a director of hardware engineering program management at Microsoft, and I primarily lead the end-to-end programs on HPC and GPU AI.
I'm Pradeep Dubey, part of Intel Labs. We look at emerging workloads. AI is clearly one of them.
Thank you. Hi, I'm Jahangir Hassan, and I work at Meta. I'm part of the network infrastructure team with a focus and emphasis on AI workloads.
Hi, this is Surendra Anabolu. I'm at Broadcom. I'm in the switch group. I focus on the switch architecture and focus on traffic loads, characterization, testing.
Hi, folks. David Weatherall. I'm from Google, and I work on data center networking of various flavors, including what we do with our GPUs.
Hi, I'm Frank Helms. I'm AMD fellow, senior fellow, and I'm the staff architect for the Accelerated Computing Business Unit, focusing on HPC and scale-out distributed training.
Yeah, I'm Whitney. I'm a hardware engineer tech lead at Meta. Okay, so maybe let's get started. Yeah.
Okay, great. So maybe to kick off this panel, we'll start a little bit by orienting ourselves with what are the large-scale AI challenges that a lot of the companies that are deploying hardware at scale for AI are facing. So maybe I'll open it up to the panelists to start discussing what they see the trends and what are the key challenges they see.
Do we take turns or
yeah,
jump
sure.
in? All right, I'll speak on behalf of Meta. So we see sort of a few different challenges emerging in the AI infrastructure. One of the primary ones is just the raw I/O requirement from the accelerator device down to the wire, both in terms of the throughput and the latency, and their hardware issues as well as transport issues. And we see this, it's a problem today, but we see this exacerbating as the years progress. Power and cost is another angle on the networking side, where we have networking devices that may not have been engineered for AI. They may have a lot of bells and whistles that are not necessarily needed, but that's what's commodity, that's what's available. And so that does affect the power footprint. I'll pass this on to David. Do you want to?
Sure. Thanks, Jahangir. Thanks very much. So I'm a networking guy, so for me the challenge is networking, right? Of course. But I mean, seriously, I think that, you know, we know that these ML training jobs are very tightly coupled across GPUs. And as you grow the number of GPUs, the network is right there in the middle as a critical part of the computation to sort of speed it along. So, you know, you're going to need heaps of bandwidth, so scaling the amount of bandwidth you have there and the size of the GPUs while keeping everything low latency is a big overall challenge. I think there are lots of aspects of that challenge, from the hardware down, you know, up through the software stack. But maybe just to pull out a couple of things for the discussions, and I'm sure different panelists will touch on different things. One thing I'd pull out is isolation. So at Google, one of the things we do is we work on Ethernet-based solutions for scaling here. And no matter what solution you have, whether it's Ethernet or not, all of these computations are, they're often collectives across the GPUs, some kind of computation involving many of the GPUs, or all of them. And so they're very vulnerable, performance is very vulnerable to stragglers. Someone's slow for some reason, then the whole job slows down. So it's very important across your networking solution to have good isolation all the way from the NIC and everything that's going on. And this includes in all of the transports and so forth, so that you don't have congestion hotspots that slow some senders down and slow everything down as a result. So that's one thing I just sort of throw out there to think about. And another one, maybe just to mention very quickly and then hand off, would be reliability, or really fault tolerance. As these things get bigger, components will fail. And the solutions we have today aren't very graceful when that happens. You can lose a lot of work, really the job stops. You know, you can checkpoint occasionally, but it's still very expensive, and failed components can take a lot of equipment offline. So somehow we need to work out how to handle these sort of failures more gracefully to tolerate them for the job.
Okay, I think great insights from both Jahangir and David, right? First, I want to talk, something positive. This is a good challenge to have. I mean, today we are able to ship regularly supercomputers, right? I mean, for example, this year we have these ND100B4 which we have shipped, and topped in the top 500 list in June. I mean, before it used to just be in government sector, right? Like now there's public, supercomputers, so which is a great problem. So I think this is a great panel to discuss that. I agree with both the challenges we have, but along with that, I mean, obviously the amount of power, the megawatts we need, in running these clusters is definitely a huge, challenge, because it's not as easy as running a simple compute cluster. So that's a place where we all, definitely need to invest more innovation and, strategy and, time and engineering. Along with that, I also feel another challenge is because these technologies are so fast, we are developing so fast, we are shipping so fast. The firmware updates, which take a long time in the data center, I feel is a very big challenge. And obviously, we have a laser focus on customers, so we don't want to have any impact on not have any interruption of their usage. So I feel that is one of the big challenges, along with the current challenges we have in the supply chain industry, whether it's lead times of getting the silicon on time to be able to test it faster and having scalable results before we actually deploy them. I feel these are all the challenges in addition to what they both have mentioned.
To Salarja, your point is more like operational point of view, right? There are many challenges. And after we deploy to data center, how we can do the maintenance and the service.
It's not so much the maintenance either, because while you're finding things, you want to be able to update, so you don't have any bugs and stuff like that. Right. So yeah.
I think it's an interesting point you bring up about now some of these AI supercomputers being made available to the public. I know at least between Google and Microsoft. How do you think about offering AI through your clouds, and how is that in terms of a challenge at scale relative to maybe your own internal use cases? Do you see additional challenges in terms of making AI available through your public clouds?
Okay, not quite sure how to answer that, but yes, it's hard. I mean, so that's definitely a goal. Of course, I mean, all sorts of aspects come up here. If it's your own network and setup you're building, you know exactly where everything is, and you can lay it out very well for performance. When you're seeing things through the cloud, it's virtualized, so we need to take care and be able to provide people the setups that they want, which are carefully organized, sliced out of the overall pool for good performance. So that would be one example of something. And of course, there's an underlying physical pool of equipment, so making sure that there aren't interactions between different customers would be another.
Mm-hmm. Yeah, I would agree with that. I think performance and capacity and ensuring things are running smoothly.
I see. So we just actually hear a lot of like challenges from different angles, right? Which is good. Then next question, I'm going to ask the supplier provider, like solution provider, like from Intel, from Broadcom, and AMD, right? Even NVIDIA as well. So those are good challenges to have, like Largescale just mentioned, right? So what are the some of possible like innovation like we are working on, what we think we should work on? Yeah, maybe start from, yeah, Pradeep.
Yeah, so the big problem with AI or data or AI training is really data, right? And it's although we talk about it quite a bit, but we are highly inefficient in how we store data, move data, okay? And we are reaching a point where compute is never the issue. It's really the feed and scale which has become the bottleneck. Like I think you were also David just mentioning. So I think in terms of where we need to focus as solution technology providers, we need to focus on the movement of data and the processing of data and the prep of data, right? Most people spend time sweating before they do training and they're even embarrassed to admit it. So they all talk about the exaflop of training flops, but it's nothing to do with flops. It's the pre-flop stage where you're just doing additions, okay, or sorting and comma parsing is where the sweat is. So we have to really focus on the data prep data, and that data-centric approach to training will actually get you much more ROI than the model-centric where we've been growing and deepening and widening and burning flops and seeking solutions. But it's not a scalable path. So I think in terms of where we are, we can be better spent innovations-wise, right? We need to be looking at that ingestion, the storage, the movement, the data prep, data pre-processing part, which will much more output ROI.
Right. Great point, data ingestion.
Sure, yeah. Maybe, yes, Surendra. Yeah.
Yeah, I think I'll add something more to that. As Pradeep said, I think there is issues in the front end. And in the backend network as well, the bandwidth is growing a lot. Like Jahangir said, is like the amount of data that like each node needs is a lot. And then, and also you need fairness of access, as David was talking about. So the bandwidth is definitely, like if you look at the many years ago, like 10 years ago where we started, the bandwidth is growing maybe about 2x in every generation, which is every 2 years. Like let's say 10 years ago we had Trident 2 with terabit per second. Now we have 25 terabits per second. But that's not enough. I think for the AI, the bandwidth is growing even much faster than that. Yeah. But I see that actually I think we need to keep this innovation up and keep moving the speeds up beyond the 25 Tbps. But it's not just that. I think we need newer architectures in the fabric so that it scales well for the data patterns that we have. I think that's, so we need to be able to scale up both from the component and also from the fabric point of view. And the other third angle I want to bring up is the one that, especially the point that David brought up, that's very near to me, dear to me, is that how do you make sure that it's not just that you have a large amount of fabric bandwidth, but they all have fair access, they all finish about the same time. There's no point in having like most of them finish and then there's a straggler that's coming back. So how do you have fairness? And there's also a place where there's a issue of a concern right now because there are a lot of proprietary congestion algorithms out there right now. So even though you talk about Rocky V2, but above that, there's a lot of that is there. And the last point I want to mention is the power, I think, power and energy, yeah. Right? So you have seen earlier, Omar was showing us like how the heat sinks are getting larger and where we go to liquid cooling. But even then, I think that's going to be a big issue. I think right now, if you see generation, there's 20-30% of power improvement. We need to look at how we can make it energy proportional and how much is the useful capacity of the fabric that you have per watt of power, like how many TVPS for useful TVPS per watt of the power.
Yeah, I have some follow-up question. Maybe I'll let Frank go first.
Sure.
I want to ask some follow-ups.
Yeah, thanks. I have a few thoughts. So one is we also need to work on getting to like the next lower precision because I don't want to say that's free, but if you have fewer bits of operand and you have fewer bits that you're multiplying, it's going to be lower memory bandwidth, lower memory footprint, lower dynamic power consumption. So that's another way to improve throughput for compute without expanding the power budget. Second of all, we are increasing I/O bandwidth, memory bandwidth, through the entire hierarchy, memory subsystem through caches, et cetera. We're increasing the number of flops for a given format, generation over generation. Process technology, as everybody knows, is no longer scaling the way it used to, and so basically that means things are getting higher density from a power perspective. And so I think there is a big thermal problem that needs to be addressed. We've got to get to solutions for higher density, even just on an SoC level, but you can expand that out to a rack level. And then the other problem that we have is, from a network switching perspective, my understanding is we're going to be at 800 gigabit from big Ethernet switches in 2023, but the endpoint NICs aren't keeping up with that. And you can sort of see why, if it's general purpose, 2-socket, x86 CPU, okay, maybe you don't need 800 gigabit NIC for one of those, but we just had this discussion. Distributed scale-out AI training is going to be bottlenecked by that. So we need to get on to getting the endpoint NIC to match the fastest switch port. Yep.
Okay. I do have some follow-up questions. So Pradeep and then Surya, you just talked about front end and back end, right? We do have bottlenecks in the bandwidth, for example, right? We need a higher bandwidth, even for the data injection part, right? If the bandwidth is not keeping up, right, the data just not be able to get in fast enough. So this is a problem I actually see. For example, we are relying on PCIe standard today, right? And then later going to be CXL. It's a good thing, right? But what about the bandwidth itself? Currently, PCIe is actually slower, much more slower than the backend. So backend, we are already today we're talking about 112 gigabit per second. I think earlier section we're talking about the high speed. Making the faster speed, right? The challenges for the signal integrity, for example, right? But now let's back to the front end. So they are actually not matching each other. And then when the compute get a lot more, memory bandwidth get a lot more, and then the data injection path is actually a bottleneck will be there. Yeah. So that's, I think, is there any thoughts on it, for the front end bandwidth related? It's also about the protocol itself.
I mean, it has to be taken at, looked at all angles, so at all levels, I mean, right? So we have been looking at the ingestion part, also algorithmically how you can do some processing there to bring it down, right? And clearly compression gets talked about quite a bit. Ultimately, there needs to be a technology angle to this. That's why we are all here. Right. And the biggest problem with data movement today is that it's 10 picojoule per bit, right? And therefore, the moment you start moving things at terabits, you just blow up your power budget, right? Thermal budget. So that's the biggest issue. Now, how do we bring it down to 5 and then 1, which is where we all become enamored with photonics? It's clearly there's hope, right? So ultimately, the longer-term solution to this is those twofold, right? First, really figure out minimizing data movement, doing compute in the fabric, in the switch, in the NIC, right? The minimal, and AI offers that opportunity, doing things hierarchically. But ultimately, we are all counting on the technology, and there are some really promising technologies which.
Yeah, I just heard about photonics. How far away for these technologies right now?
So maybe I can add some more to that. Is I think right now we have 200 gigabit NICs that's based on PCIe Gen 4. I think I can see PCIe Gen 5. You can get more.
It's coming up. Yeah.
And then the couple of other ways to look at it is maybe one is photonics that you mentioned. There's a co-packaged optics that can get you to high speeds, but I think that's a little bit further away from the NIC itself. The other way to look at it is maybe the accelerators. I already see the trend. I think you probably see it in the news, right? Like some other accelerators, they have the Ethernet interface built right onto the accelerator itself. That reduces the amount of power that you need to take. And if you don't have that, then of course you have to go to the PCIe, which PCIe can actually drive. Right now it can drive 200. I think I can see it can drive to 400 as well.
Yeah. I see. Okay.
I just want to add one more thing. When you talk about lower precision, such things, I mean, yes, at the end when we are computing, but if you brought in junk for so long, right, and then at the end, if you, whatever you do, it doesn't really help, right? It has to be addressed right up front when we, and increasingly AI has to deal with sparsity, right? Dimensionality keeps growing. So you bring a page and we pick a byte out of it, that's picking a byte at the compute is least of the problem, right? The fact that you're fetching a junk and throughout the system, right, that's where you're burning power hugely. So some smarts have to be put up front and
I think from a technology provider perspective, AI ML is a fast-moving area. So how do you see maybe end users can help you in terms of being like workloads or simulation environment, in terms of helping design next-gen technologies optimal to use cases? Are there simulation environments? What are the different types of things that you would, as technology providers, ask of the end user community?
Yes, I think.
No, go ahead.
Go ahead.
Yeah, so the simulation is actually a very useful platform because we depend on that. Like there's a development cycle that takes, and we need to understand the traffic and workloads very well. And in the cloud business, it took us a little bit of time, and then now we are there because it's been stable for the last 10 years. AI has different traffic workloads and data patterns, like all reduce or all to all, and then of course the sparsity, what it implements. So it is hugely beneficial to have standard metrics, benchmarks that are available where the technology providers can use that as a reference and can both for development and also to compare solution to solution, how they perform.
Thank you. And just to add to that, Surendra has already been asking for workload traces, just for this very purpose, so that you could check things against them and see how well they work.
I guess I'm going to add a plug here for Meta. Then we have shared some data with some of our partners. I know with AMD, and I don't know if that's happened with Broadcom as well. We have traces of AI training workloads sanitized, and then we've shared with some close partners to evaluate next-gen technologies.
I always like to tell technology partners, we are happy to provide you workload and traces information as long as you will not hold us accountable for it in 2 years, because sometimes our software engineers move much faster than semiconductor cadences. So I think there is certainly a give and take there between technology providers. So you can't necessarily come back and say, hey, you told me this is your workload 2 years ago, but then your engineers thought faster. So as long as we are pretty nice about it, I think there is definitely a way to work towards that.
That's actually a really good point. I just want to piggyback off of that. Traces can be misleading because you're looking at packets on the wire, but what packets on the wire tell you is really there's a collective running at maybe the TensorFlow or PyTorch level, and there are multiple layers of software between that and the wire that is actually interpreting the computation and translating it into data transfers. And how you implement those collective libraries has a huge impact on what's actually going to show up on the wire. So if you're just looking at traces on the wire, you may get a false impression of what's actually going on. So that what I'm trying to say is that just blindly looking at the traces is not sufficient. And that's advice for all of you looking at this data is you also want to understand what does this trace actually represent at the communication pattern level.
Yeah, totally makes sense actually. Thank you.
Yeah, I mean, see, AI is not H.264. It's the fastest moving thing algorithmically.
Yes.
Anything that moves so fast algorithmically, looking at traces is absolutely the wrong thing, right? But there are still motifs that are more last over longer time and longer period. So Resonant is already Black Scholes, right?
Yeah. So yes, it's moving really, really fast. How fast it is, and then Rob is not here, but we do see NVIDIA is driving like almost 2x, right, of the speed, of this interconnect speed or the bandwidth, like 2x every 2 years. And then actually, my question is how we can keep up of this, right? So today we're running 112 gig PAM4 right now. And then, so we are running the OI group. We already see problem like a signal integrity problem by supporting these 112 gig with the electricals. And then, so I'm wondering, like moving forward, right? Like 224, what is the plan, right? What is the plan for the future, and for like such high speed kind of thing? right? Maybe Frank and Surendra, you guys can share.
Yeah, I mean, we're going to have to work together as an industry on optics. I mean, that's apparent, right? I mean, it's not immediate, but eventually to enable those kind of bit rates, yeah, we're going to have to work together on that. You know, I guess in the near term, which would be through maybe 2025, it's probably going to be pluggable optics. But certainly the work has to happen up front now to enable, you know, co-packaged optics and that sort of thing. I gather there are a lot of challenges around testability, reliability, et cetera, for co-packaged optics. Those things need to be worked on in order to make that ready for prime time. So I think near term it's pluggable optics. Longer term it could be the co-packaged optics. But certainly eventually we're going to have to bridge the gap. Yeah.
Yeah, I can add to that is that so the 200 gig is inevitable. I think it's not right now. The 100 gig is going to serve us well for some time. But if you want to increase the density,
right,
then you need to get to the 200 gig. I saw a poster somewhere here on the OCP as well about the 200 gig, the validation. So that is coming. And then the co-packaged, I see the co-packaged as very valuable, not only just in terms of increasing the density, but also in terms of lowering the power. So if you just look at the amount of power and the power density, the co-packaged optics save significantly. And there is different platforms. I think, of course, we are working with Meta on that one. So I think the combination of the two, the co-packaged optics and also 200 gig will happen.
Looks like we are actually approaching the problem right now, right? And then get more and more close. And then we'll see if industry going to come out the workable, deployable, like a co-package technology. Yeah,
that's one place I actually think OCP can help, can contribute to that. I think right now in the OIF, CPU co-packaged optics standardization is moving along. But I think we could, as part of the UBB or as part of the extension of the OAI, if we can integrate those interfaces.
Yeah,
I think
good point.
As AI kind of grows in scale, there are, maybe I'd like to get perspectives from end users here around how do you think about balancing like performance, power, cost? Do you see this AI at large scale kind of segmenting into various types of usages, or is it something that you think is going to be largely emphasized on performance? So how do you see the trade-offs as end users as AI proliferates?
I'm going to go out on a limb here and sort of propose a optimization metrics, which is watts per flop. Right? So performance by itself, I think, is not sufficient. Like you don't want to just blindly optimize for performance at whatever cost, right? So I think that is how I would lay out the problem. Is you've got a certain number of accelerators, you need a certain amount of interconnect to drive them, and a certain number of watts to compute that, right? So in the end, it matters. Like I have a model with, let's say, one terabytes or whatever, and how many watts am I burning to train that model, regardless of whether it's 10 GPUs or 100 GPUs or whatever line rate.
Thanks, Jahangir. And I just want to throw cost in there. I mean, for all of our users who are using the cloud, they very much care about cost performance as metrics. And that's quite different than what we might like to do just as, more on the technology side, building the very best, fastest thing we can, cost no object sort of thing. That doesn't always serve our users well. We want to understand what that path is and get enough performance. But we also need to make sure it's very cost effective. So that's a big consideration.
Yeah, I agree with that. I think performance, cost efficient performance, I think is what we're looking at.
I see. Okay. Maybe let's also switch to the other question I have. It's the kind of like the panel discussion for today, right? The open and then interoperable interconnect, right? So currently for like scale out, for example, we actually see scale up and scale out many different transport protocols that's running, and a different company may have a different preference, or different company are working on different technology, right? So what are the view from solution provider point of view, from end customer point of view, right? what are the views like for those things? Because there are different options, right? And like, what's in your mind?
Yeah, I think definitely having more standardization, right? Having more vendors, innovating faster, accelerating the innovation, and having some form of standardization, because you don't want to reinvent the wheel, every few months, right? Like everyone, we have few vendors who are, obviously leading the industry, but at the same time, how can we, is there a place where we can maybe reuse the platform, or can it be a plug-in, and then can you leverage what you have learned from your previous generation and a lot of it into the next? I mean, how can you make that, a little bit easier, for us to be able to adapt to new technologies faster? I think is what I would say will be extremely helpful.
Can I jump in here and just wanted to add a little bit of color for the audience's benefit, is that what we're seeing at hyperscalers is that the need for high performance is driving this very tightly coupled, deep vertical integration that I've got a certain type of accelerator, this is kind of GPU, it can only work with this type of collective library, it must pair with this type of NIC, and then that NIC will only work with this type of switch. And we're making those decisions because that's the path to get to the performance and power that we want. And I think what she's trying to say is that it would be nice to be able to switch out these components in a sort of plugin. So a good analogy here, and then I'll hand it over to David, is in the Ethernet world. So that's the end goal that I would like to see, is can we get to an HPC equivalent of the Ethernet world?
Thanks, Jahangir. I mean, that's just where I was going to follow up on, actually.
Okay.
Well, because I think there is an opportunity there, sort of on the OCP side. I mean, so if you look at the internet, the networks, you sort of build for these things. There are really a couple of different approaches. There's sort of InfiniBand-based solutions. Google tends to favor some Ethernet-based solutions for a variety of reasons, around ubiquity and cost-effectiveness and data ingestion, for combining sort of all of these things together. But if you look at that space, there's a little bit of a gap in terms of open, standardized solutions that people can use there that are very effective. There's, of course, a line on Rocky, which has improved over various iterations. Originally, it didn't work very well because of things like pause frames, lossless Ethernet, and so forth. And while it's come a way, we feel that there is still a lot to be gained by sort of having better solutions there, and by making them sort of a little less proprietary. You can tend to get into all of the proprietary extensions to Rocky to make things work, which sort of goes down the path that Jahangir is talking about. X only works with Y and Z. So I think things can be a little more relaxed there. Just to throw something out in that space, just a couple of weeks ago, Intel and Google announced that they're working on Mount Evans, which is an IPU, just think a network chip at the host, and that will have RDMA. This is all publicly announced before, so I'm not telling you anything new here. But that will have RDMA and a new transport to allow it to work over Ethernet. So that's just an example of one area we're interested in, sort of pursuing better solutions there. Google's also said that it intends to standardize and make that solution there open. So that would be one thing that might be available in the future. I'm sure there are others in this space, but I think this space is ripe for doing something.
Yeah, and I would add to that AMD is definitely interested in having, an open standard, multi-vendor, interoperable solution. And to tie this discussion into the one that we just had about, hey, eventually it's going to be co-packaged optics, that means you have to have an interoperable standard that works for every vendor, so that every vendor's endpoint can interoperate with every vendor's switch. And we're only going to get there if we do it as an open standard. So we're absolutely interested in collaborating on that. And Ethernet-based seems like the obvious choice.
Yeah, I mean, Nothing to add, really. I mean, Ethernet, absolutely. There's no reason to deviate from that standard. There are limitations which can be evolved and fixed and addressed. But AI has become a little bit too much of a wild, wild west, right? And the numerics is no different, right? There is no IEEE for all kinds of emerging formats. It does help, but it also hurts, right? Especially also same thing with networking, right? The scale up and scale out they don't need to be thought completely differently at the protocol level. And it's what point we keep missing. Of course, it's the cost, hardware vendor cost, but the bigger cost is the programmer's cost. It's hugely painful, right? To unnecessarily be worrying about such things. And if a network trained once doesn't converge because of silly numerics mismatch, same thing, protocol differences, proprietary stuff, the pain that the data scientists and the practitioners feel is humongous, and it's on an ongoing basis, not just once you just sell the system, but people suffer through it throughout. It's hugely costly.
Switching gears a little bit, I know Pankaj and Chris Malone talked a lot about like how future AI platforms are getting into the thousands of watts and things like that, right? What are your all thoughts around things like how to deal with high density, high power going forward, and what type of work should the OCP community focus on in this space going forward?
I think, there are several presentations today and even in the expo hall yesterday, right, talking about, liquid cooling and facility water. These discussions are going on, but I think, we know that is some step we have to take, but I think there are challenges, right? How do we ensure we have all the validation and the testing, done, and to ensure, before it goes into data center, you have full, complete confidence, and because air cooling has been there for so long, but that's eventually we have to, to cool these highly dense silicon, we have to shift gears. So I think everyone's working in this space, but I think, and I know that there is, even in the stream, you have liquid cooling, right? Yep. Whitney, which is, we have a lot of discussions there as well. So I think we are all having the right discussions, moving in the right direction. But I don't think we have solidified, clear answers yet. I think we are moving towards it. That's what I would say.
I just want to add one thing about liquid cooling. I think one of the challenges with liquid cooling is the agility with which you can deploy it. It requires a lot of sort of work up front, and then you dedicate certain rows in your data center that these shall be the places where I will have liquid cooling, and you have to know that a priori, sometimes even years in advance, and then that's not flexible going forward. I have only 6 rows, and if I'm not using all 6 of those for AI, now you've stranded that power cooling. So I think that is having the flexibility to deploy liquid cooling when I want and where I want, I think is going to be a very interesting problem to solve.
Oh, yeah, very well said. I agree.
Yeah, and I'll echo that we definitely have a thermal density problem. If we're doubling just from hardware, I know there's more to be had from software, but if we're doubling the hardware throughput, memory bandwidth, I/O bandwidth, computational throughput every generation, and the process geometries are getting a little bit smaller, thermal density is going through the roof. AMD publicly announced 8-stack HBM product this week. It cannot continue forever without improvements, right, on the thermal solution, and I think the OCP community can certainly help with that, and I'm not trying to be prescriptive about any particular type of solution. There just needs to be effort and work there, and together we need to figure out what is the way forward, because I don't know, 4,000 watt accelerators might not be a thing. I don't know.
I think we could probably keep talking, but maybe this is time to open it up for the audience for any questions you may have for the panelists.
Yeah, we can open to the audience to ask any questions. Yeah.
You mean in the network in particular, sort of thing? So I mean, I'm close to transport issues, so naturally I see everything in terms of transport issues. But another thing there, just you know, beyond the protocol itself, multipathing, just the pathing across our networks. So in particular, for some of these ML training jobs, you would want a relatively small number of very high bandwidth connections. And just the way a lot of transports work, they don't work so well at having the single connections go at the blazing rate. So that's an issue on how to deal with that. Really, I think that means that things get split up into multiple sort of sub-connections in some ways. But the right protocols to do that, and also the right transports to, well, actually the right way to combine the jobs, the way they use networking with what's down in the network. I mentioned isolation briefly. So, you know, you want to avoid congestion hotspots or anything that's going to cause you to be stragglers. But when you've got all of these collective ops running on top, you know, often they're not as aware of the topology as they could be. If you're talking to people within your own rack, you just have much better isolation than if you're talking, you know, all the way across and, you know, possibly competing with lots of other people. So I don't think a lot of the collective ops leverage that as much as they could to provide isolation all at that level all the way through. You know, I think it's more there than sort of primitives in the network work like quality of service. There's a lot of stuff you can use there.
Yeah. David, do you mind if I add a little bit of color to that? One thing I wanted to make sure that the audience is aware of is that so these high bisection bandwidth fabrics, typically the way they're implemented is you have many different paths to get from point A to point B. And you know, a typical solution is ECMP, where you apply a hash, and then everything in that flow takes that one path. And we do this because endpoints don't like receiving things out of order. So the ability to receive things out of order is actually a very powerful tool if we can build that. And the reason why ECMP doesn't work as well, like David said, is that there's a tail latency aspect to all communication. So it's the balls and bins problem. If you have 30 balls and 30 bins, chances are, if you hash them, there's going to be some collision. You're not going to get a one-to-one. And then that collision is going to determine the performance of your AI workload. And so the interesting problem to solve here is either better load balancing on a per flow basis, packet spraying, maybe reordering on the end host. I think those are all useful tools that we should look at.
Yep. Yeah, that was great. That's what I meant by multipathing. So thank you for a much more coherent explanation of some of the issues. Yeah, and just a plus one on the handling data out of order. Yep. I mean, eventually it will be sort of essential for systems to really, truly scale.
Thank you. Yeah.
So thank you very much. This is a great panel. I should introduce myself, Catherine Schmitke, also Meta. And my question is about prioritization. We've been hearing about challenges that you're going to face in moving up Whitney's performance ramp. So how would you prioritize them? Is it power consumption, energy? Is it what's available within an accelerator in terms of performance, or is it thermal load, or is it bandwidth and communication? I'd like to kind of get a sense for where you think. Maybe it's different people have different opinions. That would be interesting too.
Yeah, I guess I'll start with, you know, there's like 3 pillars of AI: compute, memory bandwidth hierarchy, and interconnect. And unfortunately, you can't really pick between them. They need to scale proportionately. And like I said, you know, so I think the Scaleout Interconnect is definitely one that needs to be addressed, especially if, you know, I think I'm not a hyperscaler, so I probably shouldn't say this, but you need to take the best utilization of any optical fiber that you're provisioning in a data center, right? And that means if you can send something at 800 gigabits, you need to use that optical fiber to its fullest bandwidth advantage. And so having endpoints that can't actually take advantage of that fiber seems like a problem. So we need to get the endpoints to be able to take full advantage of whatever the fastest switch ports are of the day. And then the other problem that we have, like I said, is thermals are a problem. We've got to figure out how to address that. And at some point, we're going to have to just go to more accelerators, right? There's going to be a limit to how much one accelerator can be, what can be cooled for one accelerator, and at that point, you got to go to multiple accelerators, which is just going to exacerbate the interconnect problem. So unfortunately, I can't really prioritize it for you.
Okay, well, the order that I think I heard them in at least is that an appropriate prioritization? I heard bandwidth interconnect, and then thermal, and then the processing capability of the accelerator, because you need to go bigger then.
Yes, but I think one point that Frank was trying to make, I mean, unfortunately in these systems, you sort of need balance across all of them.
Yeah.
So whatever component is really lagging, it's just going to hold the whole system behind.
Yeah.
So it's going to change a little bit around, but we sort of need, I mean, I think that's why this is so challenging, that we need to work across that whole frontier to move it forward.
Yeah, I think, I mean, you're only as strong as your weakest link, right? So I think it's an ecosystem, right, as a solution. So I think in that, I think that you're saying all three pillars are needed, right, for us to,
It's a great answer.
I wanted to add a little bit of color here. So based on, so this is just my personal opinion, I would put interconnect sort of at number one, like said earlier. But I do want to sort of clarify where that's coming from, is that the technology that we have today and the technology that we see coming down the pipeline, this answer is based on that, but things can very easily change. And I want to give you an example, is that today, if I can overlap my computation with communication, the amount of computation that I do per byte of my tensor in the training data, that can very quickly change the answer to that question. Today, I don't do a lot of computation, so I'm not able to hide all of the communication behind computation. But tomorrow, if I start doing a ton more computation per byte, I can hide all of my communication behind computation, and then interconnect is no longer a problem. So the answer to your question could change. Like what we know today, I think interconnect is the answer. 5 years from now, I don't know.
So as part of the hierarchy of importance, I didn't hear cost. So is it problems are so important to solve that you're willing to balance everything but throw money at it?
That's a good point, Phil Mac, I would say.
I think
it's really not the, I keep saying it's not the cost of the system, it's the cost of programming the system, managing this is software cost. The human cost is huge, which and the minimum level of open software has to go with open hardware, right? Without that, this problem is already out of control. Okay.
One programmer and the entire rows and rows and rows of equipment.
Yeah. I mean, you can buy a teraflops with $100,000 can buy lots of flops, but not one programmer.
Yeah,
I think we're being asked.
I think we're out of time.
Maybe take a last question. And then,
can I?
Yeah, we can do one.
Just follow up for what Dave said. Well, I think in the network side, we do a lot of co-packaging study already, right? So like you said, well, the challenge will be which one is the slowest one, right? For example, like accelerator today, it didn't see too much work about the co-packaging optics there for communication purpose, directly going to the network chip. Oh, by the way, I work for Meta, SI engineer on both network and AI training platforms. So working on a little bit both system, but through the communication, if we can just in the accelerator side, we can engage on the CPO study a little bit more aggressively compared with the traditional switch side. I think that will be a win-win, right, for both sides. What are you guys' opinion, especially you guys from accelerator background?
I mean, yeah, we absolutely need to do it because it's only a matter of time, right? And if we don't start soon, that's just going to defer when it can be available. And we already talked about 224 gigabit per second SerDes.
Yeah.
So yeah, I mean, the work has to start very soon.
And the switch side, there are right now there is co-packaged optics available on the switch side. I think it's the accelerator side. It's still not there, but I hope to see it in the 200 gig generation.
Right.
Yeah, I think Thank you. We may need to wrap up because the time is up, but this is a great discussion. I think we have come out something like OCP can help to standardize the Ethernet maybe based, right? New transport kind of thing, and then we should follow up, and then we shouldn't just talk and then we go, and there should be some follow up through maybe OCP and then communication collaboration together. Yeah.
Thank you very much.
Thank you for coming here. Yeah.